Okay, great. Welcome back. And so this session we have. Are we a little late? So this session has two of my favorite people speaking. So first up is John Preskill, who, again, like everybody else here, needs no introductions.
All right. Boy. I'm delighted to find out I'm one of Umesh's favorite people. And I'm also delighted to join this celebration of Michael's many achievements. Those of you who know Michael are aware that when he speaks, he is with high probability correct. And not only that, he has a capacity to correct and prevent errors in his environment, whether that be his colleagues or a collection of qubits. So I want to talk about a particular achievement, which I think was a real milestone in both computer science and physics, and I'll provide some historical perspective on that and say something about where we are now. First, though, I want to say a little more in defense of my title. Michael Benor corrects errors. So here's an example. So it's December 2002. Michael and I are attending the QIP conference not far from here at MSRI. In fact, we were both speaking about the security of quantum key distribution, where we had quite different ways of proving security. And then there was a dinner in San Francisco, and we went in my rental car. I drove, and Michael was in the passenger seat. And I was quite excited because this car was equipped with a GPS navigation system, which was a novelty, at least for me at the time. I didn't have that in my car at home. And so I had great faith in the nav, but Michael had a keener awareness than I did of flaws in hardware and software. So he had a more cautious attitude. And in fact, at one point, the nav directed me to drive off the road into San Francisco Bay, and I obediently followed those directions. And that was when Michael cried out, "Stop!" Hence correcting my error. I was afraid that this story wouldn't capture properly the drama of the situation as it unfolded. So I asked for some assistance from generative AI. I gave the prompt, create an image portraying John Preskill and Michael Benor about to drive a car off the road into San Francisco Bay. It's nighttime, and both are terrified. And this was the result. So, you know, ChatGPT doesn't always get all the details right, but in this case, I think it captured the spirit of the occasion. Maybe Michael is able to confirm that. Another opportunity for me to appreciate Michael's ability to correct errors was about 10 years ago. I had the opportunity to organize the Jerusalem School in Theoretical Physics. It was the first time it was focused on quantum information science, and Michael served as the local organizer for that school. And there are a number of errors that I would have made, which he prevented or corrected. I think the most important was almost catastrophic procrastination. And as a result of Michael's participation, I see Patrick there too. He was the other co-director. The school turned out, I think, to be a success. Michael was one of the early visitors to our Institute for Quantum Information at Caltech at a time when we were both interested in quantum cryptography, and I benefited a lot from his encouragement at that time. But I want to tell you one more story, which was, now it's 2005, Caltech's Institute for Quantum Information hosted a workshop to bring together classical and quantum cryptographers. Michael was there. So the idea was that the classical cryptographers could learn more about quantum, and the quantumists would find out about the recent developments in classical cryptography, which they might not know about. So this conversation took place during the coffee break, because this kind of thing was discussed a lot. So what do you do when classical cryptographer so-and-so uses terminology you don't know? This is one quantumist talking to another. Well, I look it up on Google. What about you? Oh, well, I asked Michael Benor. Yes, Michael is as good as Google. No, he's better than Google. Now, Michael is eavesdropping on the conversation. So that's when he interjects, yes, I look up the answer with Google. So you see, he's not only invariably correct, but he's also very self-effacing. All right, so for my historical perspective, I'm going to start with the great 20th century theoretical physicist, Paul Dirac. You know, next year we're celebrating the 100th anniversary of the formulation of quantum theory. Dirac was one of the pioneers, and as far as I know, he was the first to clearly articulate the issue that if we want to solve the Schrödinger equation for a system of many particles, it becomes a computationally intractable problem. He said the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are completely known. The difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble. Now, Dirac was the scientific hero of Richard Feynman. So I had the pleasure of being Feynman's colleague at Caltech from when I arrived there in 1983 until he passed away in 1988. And we talked a lot about physics in that period, but never about quantum computing, which I knew he was interested in, but I had no interest in the topic at the time. But we did talk about quantum chromodynamics, the theory of the strong nuclear force, and we were both interested in computing the predictions of QCD, and both chagrined that we had a limited ability, even though in that situation as well, we know exactly what the right equations are to compute what happens, for example, when you bang two protons into one another at very high energy. And I think thinking about that issue was part of the context that resulted in Feynman formulating the idea of a quantum computer in a famous conference on the physics of information. Charlie was there. He spoke of a new type of computer, not a Turing machine, but something new, which is intrinsically quantum. And Feynman, ever quotable, ended his talk with this famous statement: nature isn't classical, damn it, and if you want to make a simulation of nature, you better make it quantum mechanical, and by golly, it's a wonderful problem because it doesn't look so easy. So now it's more than 40 years later, and it's still a wonderful problem, and it still doesn't look so easy, but I think we're making progress. Now, David Deutsch picked up on Feynman's idea and tried to formalize it by defining the notion of a universal quantum computer. And with Deutsch, in particular, he articulated more clearly what was implicit in Feynman's talk, that the extended Church-Turing thesis, the belief that anything that happens in nature can be efficiently simulated with a Turing machine, needs to be updated, that we should consider instead a quantum version of a Turing machine. And Umesh in particular made more precise this notion of a quantum Turing machine and worked with his student Ethan Bernstein. And he emphasized that this is something physicists should really care about, because this model of computation captures the difference between the model proposed by quantum physics and any possible classical model. And we know that Umesh helped to inspire Peter Shor. Peter wrote his reminiscences about this recently, and he recalls in particular that Umesh came to Bell Labs in 1992 and gave a talk about this work, which Shor found very intriguing. He said that he thinks he understood it better than other computer scientists because he took physics in college. Peter Shor was a Caltech undergrad. And we should be proud of the broad education he received, even though he was a math major, and then he took some advanced quantum physics. And that turned out to pay off down the road. Peter also recalls how he was on the stock program committee. Dan Simon had submitted an interesting paper, an algorithm for efficiently finding the period of a function of many binary variables. It was not accepted by the conference, in part because it didn't seem to have any applications of interest, but it was intriguing to Peter. And he thought about, well, can we use similar ideas to find the period of a function on the integers? He concluded that there was such an efficient algorithm and realized it could be used to solve discrete log. And a few days later, that it could be used to solve factoring as well. So this caused a lot of excitement, not as much as it might have, because this paper that Shor wrote was not posted on the archive, although the archive existed at the time. You had to be in the circle of people who were furiously communicating by email, which I wasn't really in. But fortunately, I received a copy of Shor's paper from Arthur Eckert because he thought I would be interested, maybe a couple of months after some other people got a hold of it. And I was immediately fascinated by the idea that there could be problems that we can solve with quantum machines that we just would never be able to solve with classical machines. And well, I was in a mood to think about new things, and eventually thinking about this led me to change the direction of my own research, which had up until then been focused on particle physics and early universe cosmology. Now, naturally, there was a lot of skepticism about the idea of a quantum computer right after Shor's algorithm was proposed from good physicists. One was Bill Unruh, and quite soon after Shor's preprint started to be circulated in June of that year, he posted this paper arguing that quantum computing will never work. Unruh had a good understanding of the theory of decoherence. That's the word physicists use for how quantum information, which is extremely delicate, becomes damaged when it interacts with the environment. And he argued that there's no realistic situation in which a quantum computer could maintain coherence long enough to do something computationally powerful. And another skeptic was another great scientist, Rolf Landauer. Landauer is a hero of the physics of computation. You probably heard of Landauer's principle that erasure necessarily requires dissipation. And for Landauer, the big problem was a different one, not decoherence, so much as the fact that quantum information can vary continuously. If we're doing a quantum computation with a series of small operations, each one will be a little deviated from the ideal operation, and those errors will build up over time. Even if the computer is perfectly isolated with the environment, we can't control it, was his argument. So within that skeptical climate, it was a big deal when the first quantum error correcting codes were presented by both Shor and independently Andy Steen later in 1995. And what Shor described is really a kind of two-layer scheme for correcting errors. We have to worry about bit flips as we do for classical information, but we also have to worry about bit flips in a complementary basis, which is something non-classical. So with two layers of coding, we could take care of both. And he described what we now call the Shor code, a block of 9 qubits such that an arbitrary error acting on any one of the 9 can be corrected. So that meant that if there were small errors acting on each one of the 9 qubits, we could run a recovery protocol, and the probability of a logical error would be of order p squared, and that would be an improvement if p was small enough. And that really answered the objections from both Unruh and from Landauer. So in particular, for Landauer's objection, there could be small errors, but when we extract an error syndrome, we either blow up the error to a big one or we correct the code block. And Andy Steen proposed independently a different code that can correct one error based on the Hamming code, a 7-qubit code, which has similar properties. So incidentally, I should say, especially since Charlie is here, that there was another approach to error correction, which was also being developed around the same time. Bennett and his colleagues were interested in quantum communication and wondered if, say, Alice in Pasadena and Bob in Berkeley share some noisy entangled pairs of qubits, and they want to teleport information from Pasadena to Berkeley. They can't do so with reasonable fidelity with these noisy pairs, but there's a way for them to perform local operations in Pasadena and in Berkeley and send classical information back and forth. So they could distill from those many noisy pairs a smaller number of much higher fidelity pairs, which could be used for quantum teleportation. And that's still the way we think today about how quantum networks will eventually be able to distribute entanglement around the world. So now that we knew quantum error correcting codes existed, there were efforts to construct more general coding schemes. And in particular, Shor, again, this time with Rob Calderbank, and independently, Andy Steen, came up with what we call Calderbank-Shor-Steen codes. And this was the first family of quantum codes that we knew of where one could argue for the existence of good codes, such that both the code distance and the number of encoded qubits grow linearly with the size of the code block, the number of physical qubits in the block. Though they did not have a construction, they just showed the existence. It's only quite recently that we've had more concrete constructions of good quantum codes. I don't really know why, because I didn't really have a footprint in quantum information in those days, but Steen's paper was sent to me to referee, and I was very enthusiastic. I dug up my report. I said, this is one of the most significant contributions to quantum information theory in recent years. I was excited. At least I didn't say, reject it. And then there were further generalizations. Daniel Gottesman was a student at Caltech at that time. And Shor, working with high-powered coding theorists at AT&T, they both came up with what we call the stabilizer formalism, which is the quantum version of additive codes in the classical setting. And that's still the formalism that we typically think of these days when talking about constructing quantum codes and inferring their properties. Okay, but it wasn't enough, right? Because these codes could protect quantum information well if we could do perfect recovery operations. But you're not going to be able to do that in a quantum computer. So it was really important that Shor, again, came up with the first complete protocol for doing fault-tolerant quantum computing. He pointed out that if we want to use noisy gates to extract error syndromes, there's a way of doing that that doesn't spread errors too badly, and we can repeat measurements, so we have high confidence in the syndrome we extract. And the really tricky part was figuring out how to do universal quantum gates on the encoded information. And his idea was that we can prepare ancillary states from additional qubits, and they might be encoded imperfectly, but we can verify that those states are well prepared, discard them if they're not. And then once we've confirmed it's safe to do so, we can let that ancilla come in contact with the data and in effect teleport the gate with reasonable fidelity. And that's still the way we think about fault tolerance today. Okay, so now there was a big opportunity, and this is where Dorit and Michael came in. A question that was left open by Shor, which they settled, is that once the error rate, the probability of an error per gate in a quantum computer is below some threshold value, then it's possible by using coding and these fault-tolerant protocols to attain a logical error rate which is as small as you please, and that the overhead cost is asymptotically reasonable. The number of additional qubits and gates that we need only grows like a power of a logarithm of the size of the quantum computation that we're trying to execute. So you can see how happy Dorit was about this development. And even Michael has a little hint of a smile, So this was a pretty big deal because it meant that we really could, for theorists, this was the culmination of this extraordinary 2.5-year period. Now we really believe that quantum computing could succeed, that we could build them, and that we would build them. For theorists, that was sort of, in a way, the end of the story, but of course not really. And they pointed out in their paper that we need to make a lot more progress to make these fault-tolerant protocols more efficient. Cooperberg always has a question. Oh, I thought you were raising your hand.
No, I have a question, but always? I didn't know that.
All right, you're right, I exaggerated.
So while you're giving this excellent history of science review, You had Landauer's objection about accumulation of small error, and now these last two papers are on fault tolerance.
Yeah.
But I don't know the specific history of plugging this last little hole to prevent Landauer's objection in the fault tolerance setting, for which you need the Solovay-Kitaev theorem. And for me personally, I was just really stuck on that point when I was learning this stuff until I realized that Solovay and Kitaev had figured out that. But from the point of view of history of science, how did that, what was the timing? I mean, was it there in these two papers already because they need to cite something, or how did that come in?
Well, I mean, Dorit and Michael can answer how they were thinking about it, but I mean, Shor already had the idea that there were only certain gates that could be done fault tolerantly, and that this would be a universal set. Now, the loophole that you're talking about is how efficiently can you, using those universal gates, approximate some operation of interest?
The loophole that I'm talking about is that you need the dense generation concept.
Yes.
So Shor actually did it numerically. He couldn't prove it.
Yeah.
And
We actually proved it.
no, so we together finished that in our paper. There's also proof of his that in fact it generates something dense, and then you can use the Solovay-Kitaev to get it fast.
So the answer is that Peter had already thought of the dense generation concept, which otherwise you're sunk without dense generation. You're sunk.
So Solovay-Kitaev was there, and even doing it explicitly. Yeah, that was
The universal set of gates was already known in the mission.
The issue is, what does the word universal mean? You have to take it to mean dense generation.
Yeah, sure. That was the definition.
Okay,
The question was, do you want to show that it's fast? And that was Solovay.
I see.
I don't know if you guys knew about Solovay-Kitaev.
Oh, yeah.
You do. Well, anyway, I mean, I don't mean the theorem that you knew about their work. Okay, yeah. Okay, that was helpful. Thank you. So there are many insights in this paper, of which Greg has pointed out one. Nevertheless, skepticism continued as these developments of quantum error correcting codes were starting to emerge. For example, two excellent physicists, Serge Haroche and Ramon, who were experts on decoherence, who had studied it with great success in laboratory experiments, expressed the view that it's fair to say that unless some unforeseen new physics is discovered, the implementation of error correcting codes will become exceedingly difficult as soon as one has to deal with more than a few gates. In this sense, the large-scale quantum machine, though it may be the computer scientist's dream, is the experimenter's nightmare. And I think maybe it's no longer a nightmare, but achieving scalable quantum computing for practical calculations is still a very daunting task all these years later. I don't have Solovay-Kitaev, but I do have Kitaev. So there was another development that was important, which was Kitaev, who saw the connection between topological phases of matter and quantum error correction, pointed out that in such phases, there's sort of a natural protection against error because logical information is encoded very non-locally. And he proposed a way to, in effect, simulate this topological matter with any quantum computer that has sufficiently high fidelity gates. He proposed what we call the surface code. And the surface code has two important advantages. One is that for error control, it only requires geometrically local processing in a two-dimensional layout. And also it has a quite low threshold of accuracy, about 1%, which is orders of magnitude better than the original estimates from Michael and Dorit. And at least in the near term, it's still the surface code because of those two advantages, which we think is the most likely path to the first fault-tolerant algorithms that are practically interesting. Okay, so let's jump ahead. To get this to work, we need the hardware, right? There are lots of ways in which qubits can be instantiated physically, and many of those are being pursued and are steadily advancing. We can encode a qubit, for example, in the spin of a single electron, or the internal state of a single atom, or a single photon that's in either one of two optical modes. These are all quite remarkable encodings because they involve these very fundamental single quantum systems, but thanks to a few decades of technical developments, spurred in part by those developments in the 1990s, we now can control such qubits reasonably well. And there are also more complex encodings that can be pursued. For example, an electrical circuit conducting electricity without resistance at very low temperature is suited for encoding qubits. And all of these approaches are currently being pursued, and it's important for now that we follow these different threads for now in parallel, because we don't have a clear understanding of what hardware approach has the best prospects for scaling up to large computers that really can solve hard problems beyond what we can solve classically. And it could be some hybrid of different technologies, which is best suited for some tasks. So to give you an idea of how we still have a ways to go, let's look more closely at the surface code, where the logical error rate depends on the distance of the code and also how far below the threshold of accuracy the physical error rate is. That threshold is about 1%. Let's suppose that we can achieve an error rate per entangling 2 qubit gates, which is a factor of 10 lower than that. We haven't quite seen that yet in multi-qubit devices, but plausibly we will in the next couple of years. And for some of the applications, for example, to material simulation, we need pretty deep circuits. So we might want a logical error rate of 10 to the minus 11 or better than that. And so to achieve that error rate, with that physical error rate of 1/10 of 1%, we would need a code block, because the length of the code goes like the distance squared in this case, of 361 physical qubits. We also need a comparable number of qubits to extract the error syndrome in silliqubits. So, we might be looking at of order 1,000 physical qubits per logical qubit in some of these algorithms that we're shooting for. Of course, if we can get the physical error rates lower, that will reduce that cost. But that's daunting from where we think things are going to be in the next couple of years. Now, we do have systems with hundreds of physical qubits, in particular in superconducting circuits and atomic qubits trapped by optical tweezers. But getting from there to a system, let's say, with hundreds of logical qubits and 1,000 physical qubits per logical qubit, we still have a ways to go. There is a lot of progress being made in this arena of quantum error correction currently. I'll just mention a couple of things, which are developments over the past year or so. One thing that's getting increasing attention is an idea called erasure conversion. We know that erasure errors are easier to correct than general errors. Erasure meaning that we know the location at which the error occurred. And in some cases, we can engineer our qubits so that the erasure errors are the dominant ones. And this has been recently demonstrated using both superconducting circuits and atomic qubits, and may be an approach to accelerating the advance of fault tolerance. What does what mean? I mean that, let's say there are both erasure errors and there are errors occurring at unknown locations, and that, say, 95% are erasure errors and 5% are errors at unknown locations. So occurring much more frequently. Oh, I'm sorry. Yeah. Okay, now I'll change it to most likely. Another idea which may have promise is we can take advantage of the structure of the noise, in particular in some hardware settings. The most likely errors are bit flips, but errors in the conjugate basis still occur, but at a lower error rate. And in fact, we can engineer our qubits to have that type of bias, and that in principle can lower the overhead costs. And there have been demonstrations of this kind of bias noise qubit in the last year or so. The theorists are making a lot of progress too. We know more efficient coding schemes than were known in the past, much more efficient than the surface code, including codes which have constant rate. All of these codes, however, require that we go beyond geometrically local processing in 2 dimensions. But there are big advantages to doing so. And there are ways to do it. One, which is being explored in current experiments, is that in the case of atoms held by optical tweezers, you can reconfigure the positions of the qubits just by optical control. And so you can bring different sets of qubits together. These are quantum low density parity check codes. So we need to measure check operators which have reasonable weight. The problem is we have to bring together qubits that are located far apart in the code block, but that's actually possible in some platforms. Or we might use some concatenated scheme where we use something like the surface code at the lower level and then use the more efficient quantum low density parity check codes at the next level up. And because the surface code performance is good, we can afford to do some swapping around of the qubits so that these non-local check operators are reachable. And these are all manifestations, and there are others as well, of the importance of co-design in the current efforts to achieve fault-tolerant quantum computing. That is, the hardware and the theory really need to advance together. And in some cases, with guidance from the theorists, the experimentalists are changing the properties of their qubits to make error correction easier. And on the other hand, learning from the experimentalists what they can do is guiding some of the developments in the coding theory. It's still a big open question. How are we going to scale up quantum computing to systems large enough to solve really hard problems, classically hard problems? And of course, the other big question is, once we do so, how are we going to apply that technology? I don't think we have fully satisfying answers to either question. As far as the applications go, we don't know a better answer than the one Feynman originally had in mind, I think, that we'll be able to apply quantum computing to solve quantum problems, to deepen our grasp of properties of materials and large chemical molecules. And to scale things up, well, we'll certainly need systems engineering beyond what we currently have, but I think advances in the basic science can also accelerate the path. Okay, so I've been talking about the quest for a quantum computer, but I want to make a remark that quantum error correction is a richer subject than that. It's really having an impact across physics quite broadly. And one way of expressing that is if one were asked, what are the most important ideas in physics in recent decades? Well, different people will give different answers, but I think these are 3 good candidate answers. The holographic principle, which is an idea about how gravity and quantum physics fit together. Topological quantum order, which is an idea about how to understand different phases of quantum matter when the particles strongly interact with one another. And quantum error correction, which, as we've discussed, is going to be the key to scaling up quantum computing. And what's very beautiful is the behavior of many particle systems that are highly entangled. The quantum error correction we've talked about, and it's our reason for thinking that we can scale up our control of quantum systems far beyond what we've achieved so far, and the threshold theorem is a key element of that belief. By topological quantum order, I mean that there are quantum phases of matter that all look the same when we observe them locally, a few particles at a time, but they're distinguished by global properties that are well hidden from local probes. And that can have remarkable consequences. In a topological phase, for example, it's possible for an electron to split into multiple pieces, each carrying a fraction of the electron's charge. This, as Kataev realized, is closely related to quantum error correction. The global properties you can think of as the logical information in a system of many particles, which is hidden from the environment, which interacts with the quantum system just a few particles at a time. And the holographic principle is the idea that all the information contained in a three-dimensional region of space is encoded on the two-dimensional boundary of the region, despite the way things appear. And this is really our most important clue about how to reconcile quantum mechanics with gravitational physics. I think Umesh will speak about this later. And here again, quantum error correction is a central idea. We've come to understand that the dictionary that relates that three-dimensional bulk physics to the two-dimensional non-gravitational boundary description of the same physics is really the encoding map of a quantum error correcting code. And the robustness of the emergent bulk geometry you can think of as being a consequence of the error correcting properties of that code. So really the way I look at quantum information science is that we're still in the early stages of exploring a new frontier of the physical sciences, different from the short distance frontier of particle physics or the long distance frontier of cosmology, where I spent the early part of my career. We could call it the complexity frontier or entanglement frontier. We have the tools now to create and precisely control very complex states of many particles, highly entangled states. And that's opening new opportunities for physics discovery. And it's the idea inherent in the threshold theorem that with our imperfect control, we can reach very large macroscopic quantum systems that would otherwise be inaccessible, is really the key for exploring this territory, and we have very far to go. So thank you, Michael, for your far-reaching contributions, and I hope we'll have many opportunities in the future to benefit from your wisdom and insight. Congratulations.
Thanks, John. That was a fantastic talk. Any further questions? Charlie.
Well, when you said, speaking of erasure conversion,
Yeah.
I think that it's not actually a thing you do. It means that if you thought a particular qubit was very likely to be noisy, you just wouldn't look at it at all. You'd ignore it while trying to correct the errors. In other words, you would regard it as having passed through an erasure code and being lost. Is that what you mean?
Well, not exactly. So an example is, in the case of atomic qubits, if you choose the right type of atom and you use Rydberg excitations to perform gates, because these highly excited atoms have strong interactions, if you choose the right atom, the dominant errors, they're going to be spontaneous decay of the Rydberg states. What you don't want is for that highly excited state to decay back down to the encoded zero. You know, you don't want a 1 to decay to a 0. You want a 1 to decay to the erasure symbol to some other state, which you can detect. And then you know there's an erasure error that occurred. And if it's...
So it is a physical process.
A physical process.
Getting it a recognizable sign that it's
Right.
bad.
So that you can actually see when an erasure occurs, and that's the most common thing to happen.
Thank you. Thanks. Fantastic.